What's up, guys? So in part one with Josh Souders from Copeland, we talked about the different compressors, single speed, two-stage, and variable speed. So in part two, Josh is going to talk about how the variable speed and vapor injection, that technology it's not new, but it's used in heat pumps so we can get maximum capacity in the heating cycle. He's going to go on and talk about how variable speed compressors use this vapor injection. And this is the reason why heat pumps are so effective these days if you get a cold climate inverter heat pump, and how it can heat when it's super cold outside. When I say super cold, I mean that's a very relative term. But anyway, we're going to get back to Josh, guys. This is the HVAC Know It All podcast. I'm your host, Gary McCreadie. This podcast is sponsored by Cool Air Products, Master, Cintas, and SupplyHouse.com. Go to the show notes and click on the links to check these guys out. Let's get back to the variable speed compressor. Now, give us just the basic rundown of what it is.
Yeah, so, and I'll keep this limited to what I would call like a true variable speed compressor. So not like a fixed speed compressor that's using an inverter of some sort.
Okay.
Typically a true variable speed compressor, or what I would call true variable speed compressor, it'll have a permanent magnet, a rare earth metal, magnet motor in it to kind of optimize for efficiency. But generally, I mean, you're pairing a compressor with an inverter. The compressor will not function like if you just hook up to three-phase power. It won't work without an inverter. And that inverter is sending, it's basically controlling the pulses of power that are going to the compressor, to regulate a certain speed. And depending on the frequency that's going running at, for instance, like our products, run between 900 and 7,000 RPM, like our current product, right? And so we'll send pulses at different frequencies to achieve a specific speed. And that speed, the OEM who's designed that system has correlated that speed to a specific, capacity to meet a specific demand. And so really the advantage of that is you can run exactly how fast you need to not shut off. Ideally a variable speed compressor in an ideal world runs 24, like to use your point about the digitals, it runs 24/7, 365, never shuts off, always continues to run. That's the idealized world. So you always get, you always have, whether even in heating and cooling, right? Regardless, it would continue to run and never quite meet the capacity demand, but be very close. So you have like almost no temperature swing and you get, maximum dehumidification, maximum comfort. So that's the kind of idealized world. And structurally, I think there's a couple things to think about variable speed compressors versus like a fixed speed, because it does come with its own technical challenges. And I think a big one is when you're operating over this large frequency range, right? You're operating, sometimes slow, sometimes really fast. Oil delivery becomes a major concern. Not only oil delivery internal to the compressor, but making sure oil is getting back out from the system into the compressor. So there's a couple things. So when we design our fixed speed products or our two-stage products, our crankshafts inside have a geometry internal drilled to that crankshaft that's designed and optimized for that 60 hertz and to pull oil up the shaft without, any sort of pump or anything. When you get into variable speed, optimizing that geometry becomes much more complex. And so generally you have a positive displacement oil pump internal to kind of force oil up the shaft.
Yeah, and it's only variable speed. It's only variable speed that has that oil pump, right?
Yeah, I mean, as far as I'm aware, I mean, I don't think any compressor manufacturer, I'll put it this way, I don't think any compressor manufacturer is going out of their way to add cost of an oil pump if they don't have to, like they would.
If they don't, yeah, of course.
So
Yeah.
yes, I think generally you would only see that either in a variable speed product or in maybe a different segment, so non-residential, like a high reliability requirement in like a refrigeration or a commercial application. You might see something like that, but in residential, you're not going to see it.
Let me ask you this question then, because depending on the manufacturer that gets or purchases the compressor from you guys and puts it in their unit, because I've seen this with different types of VRF and stuff like that, where it will have an oil return sort of program where every once in a while, if it's running on low speed, it'll be like, hey, let's fully ramp up and bring some oil back. Now, with the positive displacement pump, is that even necessary?
It is actually
Okay.
not in every case, but really depends on a lot of factors with more the system. So every compressor pumps oil out, right? Every compressor in the gas stream of refrigerant that's going out into, through the condensing coil, you're going to have oil, mist, vapor in that stream of gas. And so when you think of system design, we always look at like we call oil circulation rates, oil pump out, those kind of things. And so a lot of times what you see with variable speed is when you run really, really slow, so you're running really low mass flow through that compressor for a long period of time. What happens is you're still pumping that oil out into the system, but there's not enough mass flow in the vapor. The gas stream is moving fast enough to get it to come back into the compressor.
Yeah,
So it
to
kind
bring
of
it back.
sits
Yeah.
out, logged out in the coils. And so a lot of times the OEM will make the decision to have this oil boost cycle, as you said, where it ramps up for a specific period of time. It's run low speed for so long in order to force that oil to come back into the sump to make sure that that pump can keep feeding the bearings.
Okay, cool. Yeah, that's really important. That's a really important feature of the OEM to put into their planning and operation, right?
Yeah. It has to do with, it's all on their control logic and algorithms. Now, is obviously the OEMs are going to do all their engineering analysis and testing them, for each unique system. And it really is very system dependent. So depending on what kind of coil they're using, how big the coils are, all those kind of things can affect it. So it's not really a straightforward, like you just, you know, every OEM needs to do it, this way. They all kind of have their unique way. Now we do provide guidance, in our so we have what we call application bulletins that we publish out there for the OEMs, and we will provide guidance if they run, if you run a certain period of time at this, we recommend an oil boost cycle of some sort to bring oil back to the compressor.
Gotcha. Okay, cool. Let's talk about the vapor injection, then we'll just get in. Then it's kind of a lead into the heat pump and how heat pumps are designed to run in cold climates these days. So talk about vapor injection on a compressor and what it is and what like its function is and what it's supposed to do and all that.
So vapor injection, I think, for any of your listeners that have, they might work at, contractors that work in multiple segments of the market of the HVAC industry. Vapor injection is a technology that's been used in refrigeration for quite a while now. It's just kind of now starting to make inroads in residential. And really the goal is increased capacity and increased efficiency for heating applications. That's the primary goal. you know our our analysis and testing shows up to like a 25% increase in capacity and 10% increase in efficiency when vapor injection is on. So it's a pretty big factor. It's a way to get extra capacity out of the same footprint, you would that you wouldn't be able to get otherwise. And so the way vapor injection works is basically you're pulling gas off the condensing line. You are running it through a expansion device, and then you're running it through a heat exchanger, or you can run it through a flash tank. It can work that way too. But you are bringing that gas. You're then bringing that gas back and directly injecting it into, in our case, into the scroll pockets. So you have the normal gas that's coming from, that's coming back into the system. It's got a certain superheat, a certain, subcool. It's coming back in, going through the normal compression cycle. And then in the middle of that, you're injecting this gas into one of the pockets, the subcooled gas, to get this increased capacity and increased efficiency. And you also do
Now,
get
can
some,
can I ask you a question
yeah.
before you go on? Where is that piped from? That vapor injection gas right into the scroll set. Where is that piped from directly?
So the vapor line comes off your condenser, goes through an expansion device, goes through an evaporator, and then it
Okay.
comes from the evaporator that comes from that heat exchanger and goes straight into the compressor. There's an extra port on the compressor that it connects to.
There's people listening going, why is he calling it a heat exchanger? Because they're thinking of a furnace. He's calling it a heat exchanger because it's a heat pump, and outdoor, you can't really call one an evaporator because they interchange depending on what they're
Well,
doing, right? So
maybe I can send you maybe a graphic that you could, I don't know if you had the capability to post it, that shows kind of a simplified version of what that system architecture looks like. So there is actually an extra heat exchanger
an
that's
extra one.
inside. Yeah, it's inside the system that you use to basically, that expanded gas gets heated by the gas coming off your condensing line. So it gets
Hmm.
like reheated, and you're doing that to control the quality or the superheat, I guess you could say, of that extra gas that's going to get injected into the compressor.
The diagram would help. I'm a visual learner like most.
Yep.
So if you could send me that, that would be
Yep.
amazing. And I can utilize that as part of posting about this podcast.
You're
Okay.
basically
So,
doing subcooling is what you're doing.
okay. All right. So I'll get that diagram. Okay. So we have the vapor injection right into the scroll set.
Yeah. So as I said, that when that gets injected, you're basically putting that extra gas in there. It's a, that gas. I think there's a couple things. Obviously, as I said, increases capacity, increases efficiency. Also does help control discharge temperatures. So typically there's a limit on that discharge line temperature that we want to maintain, so oil doesn't start to break down and you just don't start to get galling and excessive wear. And so that also will help, as you move into the upper left-hand corner of an operating envelope of a compressor, particularly for heating, that's generally where you operate, is that upper left-hand corner, high condensing, low evap. It will help keep the components inside cool. It also helps with that quite a bit.
Okay. Awesome. Now, is this used only for heating, the vapor injection portion, or are they using it in cooling as well?
For residential, I would say that it's primarily only going to be used
For heating.
for heating.
Okay. All right.
Now, in other
So,
segments, I think it's used more for the reliability aspects, the discharge temperature control. But
okay.
for residential air conditioning, it will be used primarily for heating.
Okay. And this vapor injection allows a heat pump to run in low ambient conditions, just one part of it, or is this like the basic heart of how we can do this?
No, so it is just one part of it. And so, as I said, about a 20 up to 25% capacity increase. And that in particular, when you're going lower ambience and you activate that vapor injection, that is generally how a lot of OEMs are targeting those ultra low ambient temperatures. So, I'm not, are you familiar with the DOE Cold Climate Heat Pump Challenge?
I've never heard of it. No.
Okay, so a couple years ago, the Department of Energy put out this challenge, and really the goal of the challenge was to see what's possible, like how effectively can a OEM design a heat pump that is meant almost as a furnace replacement. I would say that's kind of like the target, right?
Okay. Yeah.
Not necessarily the reality, but that's kind of the goal and the target. And so they put out these targets or these requirements, and one of the requirements is 100% capacity at 5F. And what I mean by that is, whatever your capacity at your 47F rating point, 47 degree, whatever that heating capacity is, they wanted to ensure the OEM would have to provide 100% of that, that same exact capacity at 5 ambient. And so, because generally, I think, and historically, this is, what you brought up much earlier when we started off, is as you go lower in ambient, you get this kind of drop off in
Yeah.
capacity. And
Yeah.
the goal for the DOE Cold Climate Heat Pump Challenge was to prove that, through their partners in this, which are all the major OEMs, that there's a technology pathway to ensure that that fall off doesn't happen, or that it can be mitigated to a point that heat pumps in ultra low ambience are viable.
And that's funny because if you read specs on low ambient heat pumps, I've seen it where they use the 5 degree. Sometimes it's actually 4 degree, and it says at 4 or 5 degrees, basically it runs at 100% capacity. And that's after that is when you start seeing the dip. So that's all because of what you just explained.
Yeah, and this isn't like it wasn't it's not a regulated requirement or anything like that. This was just kind of a technology demonstration. But I think a lot of the the OEMs are launching or have launched products that meet that. And I think they make particularly a lot of sense in kind of like the mid-temperate areas where you do
Hmm.
get days that are in the single digits, but it's not, it's not like your Canada weather, right? I mean, they still will work very well in those lower ambients. And in fact, some of the OEMs, went above and beyond. There was kind of a stretch goal of like a negative 100% at like a negative 5 or 10 I think it was 10. And, some of them did meet that as well. And so I think you're just seeing this kind of this alignment around, or understanding or maybe a agreement that historically, low ambients were a challenge for heat pumps. And, now there's technologies and products that can actually fulfill or not have those kind of historical challenges.
What do you say to the ones out there that say heat pumps don't work below freezing? I mean, because I hear it all the time, and it's funny because up here in Canada, heat pumps are being it's like I said, it's minus. I don't know if I said this on the recording or not, but it's minus 11 C today, and I've installed heat pumps in the area, and I'm not getting calls today that the house is cold.
Yeah.
So, what do you say to the people that have this misconception that heat pumps can't heat in these types of temperatures?
Yeah, I think, one of the first things is I think a lot of people that say that oftentimes, at least when I've talked to people, it's a existing misconception or preconception they had from a heat pump they installed 15 years ago or
Yeah.
products they worked with 15 years ago. And back then in particular, OEMs just kind of, cooling was still the major focus. Heating was kind of just like, you're gonna kind of get, we'll throw it on there, you'll get what you get. But we didn't really optimized. They weren't really focused on it. It was just kind of like a nice to have that they would add on, right? And so not being optimized, not the algorithms and all that stuff weren't really optimized very heavily for heat pumps. And I think with the focus and the market developing around heat pumps, I think, all the OEMs have put a lot of focus and attention on, the comfort aspect of heat pumps in particular, and that obviously directly ties to being able to provide, adequate heat when it's really cold out, right? It wouldn't be very comfortable if you weren't getting heat. So I think there's been a lot of improvements now that obviously you still have this drop off as you get colder and colder in the ambient temperatures. You won't be able to provide capacity versus a traditional gas furnace where, it's 60,000 BTU furnace is always going to be 60,000 BTUs no matter what. It's always going to,
Yeah.
provide that much to the facility where versus, you actually have a drop off in this curve in heat pumps. It does exist. Now, as I said, a lot of that's been mitigated now. It really depends on the technology that's in the base pump as well. We've talked through all these technologies. There are certain advantages and disadvantages in heat pump applications for some of these technologies. For instance, variable speed systems, true variable speed systems generally have the capability to overspeed, which means they can go above that 60 hertz, right? Being able to do that, a lot of them run in heating, they'll run, if they're running 3,600 to 4,500 RPMs to provide capacity in cooling, they're running like 7,000 RPMs or up to 7,000 or maybe even a little bit higher to provide capacity in heating. So this overspeed capability in variable speed is definitely a huge game changer, or I shouldn't say game changer because it existed, but it's definitely a key technology that enables lower ambient heat pumps. And so, you know, I think the vapor injection is just the next step or the next extension of how do we get even more out of it beyond variable speed.
Hmm. I mean, I had a customer, and he opted out of going with backup heat or auxiliary heat. He wanted to just run and gun and see what happened. And he called me last year in February and said, "Hey, my heat pump can't keep up," but it was minus 14 Celsius at that point. So he was fine up until that point. And then, but he was still getting heat. He just couldn't get, I think his thermostat, we're talking in Celsius again, and I'll convert it to. So I think he was setting his thermostat for 21 degrees Celsius, which is around 71, 72-ish, something like that. And he couldn't maintain that temperature, but he was only a couple degrees below it. Like he was at 19 or something like that. He's just like, I think my heat pump is struggling at minus 14 or 15 or whatever it was outside C. He goes, I think I need to add the auxiliary heat strips in now. So I went back and did it for him in the fall here, just so he could. And he wasn't living in the house at the time, so it wasn't a big rush or a big deal. That's why it was done in the fall. But if you can heat a home and to that type of weather outside with a heat pump, that's pretty advanced as far as technology goes, as to what you're saying from 15 years ago. A lot of people really like the dual fuel aspect because they have a lot of trust in a gas furnace, because gas furnaces, high efficiency gas furnaces, are pretty reliable. I mean, they have a lot of reliability, and like you said, the capacity is the capacity. It does not change. So if you're ever having issues with your inverter style heat pump, you can always switch over to your gas if need be. But I think there's a true advantage when it comes to the cooling aspect, like we've talked about, when you put in an inverter style heat pump, is because you have those long run times, you dehumidify better, your comfort's better, you don't put as much wear and tear on the compressor. The argument, and I want to ask you this before we head out, the argument from a lot of technicians, installers online is, my customer doesn't want to pay the extra cost for an install like this, when there's cost savings on their bills might not reflect that over the course of time. And that's one of the arguments. I get it. There are people out there that will pay top dollar for comfort. Like, there's people out there that will, okay, I can give you a Ford Explorer, or I can give you a Ford Expedition. Which one do you want? Well, a lot of people will choose the Expedition because of a high level of comfort just driving that vehicle. I mean, they're still getting from A to B, right?
Yep.
But they like the comfort. They like the heated seats, the heated steering wheel, how it's high up, how it's the leather seats are wrap around your body. There's people that will pay top dollar for comfort. So tell me what you think about the techs that complain about the cost of install versus the customer that wants to pay top dollar for high level of comfort.
There's a wide variety of end user or customer, desire, right? But
Mm,
I think at the end of the day, even your base tier heat pumps have massively improved from years ago. And I think to your point, it is a big headwind, or roadblock for heat pump adoption, the extra cost, at least upfront initial cost. Now in areas where there's not natural gas, I think the payback is much better in a heat pump, right? If you're in,
oh,
if
for
you're in
sure.
Florida, you're not, how many days out of the year are going to run that heat pump? How many days is it going to be below freezing? Might get one or two. I mean, why would you worry about, stuff like having to deal with like an electric furnace or some of the other alternatives? Just put a heat pump, it's going to pay for itself eventually. There are a lot of incentives right now for heat pumps.
Hmm.
So I think, when you look at upfront cost, I think all the contractors should be at least aware that, there's, up to like $2,000 right now available for, heat pump, purchase as a tax credit,
More
for a
more than that
customer
in
that
some areas. We
it,
had
it
we had a
can
five
be.
or $6,000 credit last year.
Yep. So
So it
that's,
depends where you live.
yep, that's federal. There's $2,000 for the heat pump itself. There's up to $8,000 for, I think, in general. This is all federal right now. Energy efficiency upgrades. I think you can get up to like $600 for even like the electrical upgrades, or some of the electrical upgrades associated with, a heat pump install. So there's a lot of incentives at the federal level. And then to your point, there's tons of like regional and state based incentives depending on where you're at, that can really, really mitigate, the extra cost of a heat pump. For instance, you can get a two stage, or even a kind of a more budget friendly variable speed system in some cases for the price of a fixed speed system in some cases now, right? Why wouldn't you, you get the heat pump kind of as a gimme in those cases, just because there's so much
Yeah.
incentive dollars right now behind it. So I think, definitely I think most people understand that the heat pump, the initial upfront cost can be intimidating, and it can definitely be a headwind to adoption. But I think at least right now there's a lot of things to mitigate that. And so I think for your customer, as you said, there's a lot of other options too as far as architecture. We have a lot of people around our area that use propane, All right. And so,
Propane's a huge one.
yeah,
I know some people that are paying $1,000 a month in their propane bills, and I'm like, you are a definite candidate for a heat pump. And then they go, well, isn't it like $50,000, $60,000? I go, no, that's like a Geo.
yeah,
I
yeah,
mean,
yeah.
you don't need Geo anymore with the technology that
Yep.
we have, right?
Yep. And, there's several that that work with me. They're on propane. They live outside of gas delivery. And, I think every one of them's on a heat pump because they're just like, it's just too expensive to heat and cool with propane. The one guy told me, he's only ever had he's got a propane backup actually. I think he said that he's only ever had the propane backup kick on like 2 or 3 times in like the last 5 years.
Wow. Very cool. Awesome, man.
So,
All right. Well, I mean, Josh, this has been cool. I really like the beginning when we talked about the 3 compressors and how we set it up to get to where we got in this conversation. So, I mean, it's been almost an hour here of discussion. So I don't want to take any more of your time because I think we've covered what we got to do here. And I learned some stuff, audience. I hope you did, and I hope you guys stuck around to the end because this was a nice talk. Thanks, Josh. Appreciate it.
yeah, and I'll send you that graphic for vapor injection. I can send you a couple clips too of the vapor injection, how it works in the scroll, and then how a 2-stage works as well. Because I think it might be talking through it is not as good as the visual for sure.
Yeah. Yeah,
Yep.
I would appreciate. I think the audience would appreciate that visual too. So,
Yep.
thanks, man. I appreciate it.
Yep. Have a great day.